Today, we're going to dive into a mathematical tool that has, seriously, one of the best names I've ever heard, the Zig Zag Product. And it's not just a cool name, it's a secret weapon for solving problems that seem impossibly huge. So let's start with a puzzle. Imagine a graph, and really, that's just a network of points and the lines connecting them, but picture one with billions of points, like a massive digital city. Your job is to find a path from point A to point B. But, there's a catch. Your computer has almost no memory. It can only remember a tiny, tiny fraction of the map at any given time. So, how could you possibly prove that 2 points are even connected?
I know, it sounds completely impossible, right? But the solution is buried in this really elegant piece of mathematics that's all about one thing: simplification. It's a way to tame these monstrously complex networks without losing what makes them so powerful in the first place.
And look, this isn't just some theoretical brain teaser. Computer scientists run into this exact challenge all the time. We're talking about things like the internet, massive social networks, or huge sets of biological data. How do you actually navigate these enormous graphs when you're working with limited computational power? Just finding a path or checking if 2 things are connected becomes incredibly, incredibly difficult when the scale is this massive. And that's where our solution comes in. The star of the show today, the Zig Zag Product. At its core, it's a binary operation. All that means is it's a special way of taking 2 different graphs and mashing them together to create a brand new one. But as you're about to see, this new graph is something really, really special.
So the magic of the Zig Zag Product, the secret sauce, comes from combining 2 very different kinds of graphs. First, you've got the large graph. We'll just call it G. It's huge, it's messy, it's complex, it's got a high degree, which just means that every point or node is connected to a ton of other points. Then, on the other hand, you have the small graph, H. It's simple, it's tiny, and it has a low degree. Each point only has a few connections.
So how in the world do you combine a giant with a miniature? Well, the process is actually beautiful and super intuitive. It's all right there in the name. We don't need to get lost in all the formal math. We can totally get this with a simple analogy. Okay, picture every single point in that huge, messy graph G. What the Zig Zag Product does is it takes each one of those points and replaces it with a tiny cloud. And that cloud is a perfect complete copy of our small, simple graph H. So now our massive network is really a network of these tiny little clouds.
So how do we move around in this new network of clouds? Well, you follow this really simple 3-step dance. First, you zig. You take a small step along a path inside your current cloud. Then you zag. You take a big leap along one of the old connections from the original big graph, which lands you in a completely new cloud. And finally, you zig again. You take one more small step inside your new destination cloud. Zig, zag, zig. That's it. That's the whole journey.
And this is where the magic really happens. Because when you combine the graphs this way, the final product isn't just some random mashup. No, it inherits the absolute best qualities from both of its parents.
Get this. The new graph gets its enormous size straight from the big parent graph, G. But its complexity, its degree, that comes from the small, simple parent graph, H. So what do you get? You end up with a network that is just as massive as the original, but suddenly it's way, way simpler to navigate because each point only has a few connections. And crucially, it preserves its expansion, which is a key property that basically means there are no bottlenecks. It's still a super robust and well-connected network that's really hard to break apart.
I mean, that's the main takeaway right there. This is a method for radical simplification without sacrifice. You keep the huge scale, you keep the robust structure, but you slash the complexity. It is an incredible feat of, computational alchemy, really.
So, to put it a little more formally, the product pulls off 3 critical things. First, like we saw, it slashes the degree. Second, it preserves what mathematicians call the spectral gap. Now, don't worry about the term, but what it means is that the graph stays a strong expander, a network with no weak points or choke points, which makes it incredibly resilient. And third, if the original graph was all one connected piece, the new graph is too. Nothing gets lost in the process.
So, okay, this is a really fascinating theoretical tool. But what does it actually do for us? Well, this is where we circle all the way back to our opening puzzle and see how the Zig Zag Product led to a genuine real-world breakthrough. The product was first introduced back in 2000 by Ringgold, Fadan, and Wigderson, and just 2 years later, it was already being used to build these highly sought-after things called expander graphs. But the real whoa moment came in 2008 when Omer Ringgold used it to crack a famous, long-standing problem in computer science.
And yep, that breakthrough was the answer to our question from the beginning. Ringgold created an algorithm powered by the Zig Zag product that could figure out if 2 points in a massive graph were connected using only a logarithmic amount of memory. That means for a graph with a billion nodes, the memory you need doesn't explode. It grows so slowly to the point where you'd only need the memory equivalent of a few street names. It was absolutely revolutionary.
So, the Zig Zag product really has these two world-changing applications, with effects in fields from network design all the way to cryptography. First, it gives us a clear recipe to build better networks, ones that are huge, robust, and yet somehow simple. These expander graphs are critical for things like resilient communication systems and even error-correcting codes. And second, it powers algorithms that let us navigate these networks with unbelievable efficiency, solving problems that we once thought were pretty much impossible to compute.
This quote from the research just sums it up perfectly. It takes the best of both worlds, the size of the large graph, the simplicity of the small one, and the robust connectivity from both of them. I mean, it's just a masterclass in elegant design.
When you get right down to it, the Zig Zag product is so much more than just a clever algorithm. It's this beautiful reminder that when you're faced with a massive, tangled maze, maybe the most ingenious solution isn't to just charge straight ahead. Maybe it's to take a small step sideways, a big leap forward, and then one more small step to finally find your way.